My name is Evelyn Boettcher, and today I'll be talking about processing large data with a Python Pandas library. This talk is in my repository under Evelyn Boettcher, and then you go under Evelyn Boettcher CV. So the motivation of this talk is because data sets can get large quickly. So you could be looking at a few hundred rows, a handful of columns, and then all of a sudden it's millions of rows and hundreds of columns. And you might end up saying to yourself, ooh, my data's too big. I need a better computer. If that is what you're thinking and saying, well, this talk is for you. I'll show you how Python Pandas library with smart user categories can allow you to read in these really large data sets on a laptop. And luckily, we live in a time when our laptop's processing power would have made engineers in the 60s swoon. So large data has been around for a really long time. And it always had these attributes. There's always been some type of access control. Sometimes it's not easy to get. It shows what it shows. It is what it is. And the data sets will grow really large. An example of access control is like this planet data set. Tycho Brahe had, in the 1600s, the best data set on the planets. Jonathan Kepler needed that data to prove his theory that the planets orbit around the sun. But Brahe was like, no. So Kepler had to wait until Brahe died before he could get a hold of that. And to this day, people think that Kepler killed Brahe to get access to data. Luckily, we don't have any data that we need to kill for. And it shows what it shows. So you always have to take your time to understand what's going on and what your data is actually really telling you. And something is not intuitive. So in 1600, Romer was trying to figure out, made his calculations when Io will have an eclipse, and Io is one of the moons of Jupiter. His calculation was off by several minutes. And at this time, prior to his calculations, people thought light was instantaneous. But what he ended up doing was actually concluded what the speed of light is. He took the difference between the two times and calculated what the speed of light. And you gotta, admire someone that just has the willingness to say, my work is correct, and the timing is off because light moves at a finite speed, and here it is. That is amazing. So our data, typically, we think of what, it's really large, and obviously, large data has been around. And we have it a bit easier than back in the day. We have computers, namely, and we only have to deal with nans and not numbers and slow download speeds. We still have to deal with access control, but we don't have to kill anyone. And there's always Easter eggs in the data, so we do have to take time. And that's what the beauty about Python Pandas is. It allows you to slice and dice the data in unique and fun ways to see what's going on. And you always have data growth. But getting back on task, my data is big and you want to read your data on your laptop. Well, let's talk about Python Pandas. The Python Pandas library is a high-performance, easy-to-use library for analyzing structured data, so CSV, JSON, SQLite. Pandas is fast, powerful, and flexible. It enables you to quickly parse data, but it's designed to handle data roughly less than 100 megabytes. There are other tools out there to handle really large data sets, so 100 gigabytes and a terabyte. But the reason why people like to use Pandas is that it does an amazing job at cleaning messy real-world data. So how does one handle large data with Pandas? Well, when you have a gigabyte of real-world data and you want to explore it, you use your laptop, and you don't want to switch to another language, use an old programming trick and set numbers to the lowest possible bit value, so int 8 or float 16 or float 32. This will greatly reduce the memory that your data frame is taking. So the second step is to use categories. If you have, and sometimes with numbers, strings that repeat. An example of strings that don't repeat, so if you have a list string of, say, hello world, or a whole bunch of unique identifiers, those don't repeat, and categories will actually make things worse. But if you have, a lot of times you have, strings that do repeat. So you might have like the days of the week, so Monday, Tuesday, Monday, Wednesday, Sunday. This, with a smart use of this is a great candidate for categories. And let's go take a step backward, like data memory footprint. So an int 8 is numbers that go from basically from 0 to 255. So it's like 2 to the 8th, and that's where you get the 8. And that's 1 byte of memory. So numbers that go from 0 to 2 to the 16th is an int 16, and you have an int 32 and an int 64, and those take up 2, 4, and 8-bit bytes, respectively. And this is where strings come into play. One character in a string, sans overhead, takes up 1 byte of memory. So if you have a string that's like 6 characters long, that's 6 bytes of memory just for that one string. So how does Pandas categories work? Well, Pandas categories map an integer value to the raw value in that column. So if your data frame was like Sunday, 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 Pandas treats the category Sunday as a category equal to 1. So in effect, your data frame now becomes 1, 1, 1. And this is why it greatly reduces the size of that data frame. So to convert your data into a category, just simply for each category, set that type to be a category. So you go your category dot as type category, and boom, you're there. So this would convert if your category was your data column was Sunday, 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 Monday. This will map to like 1, 2, 3, 2. But converting to categories is not always helpful. The following examples will show you the power of categories and some of the pitfalls. So the examples and the following scripts are located in my GitHub repository under the Pandas scripts. Big data, if you had this data frame that I created with the int floats categories.py file of just numbers. So I have 3 columns. The numbers range from 1 to 4, and there's 10,000 rows. The first column is just integers between 1 and 4. The second column, I explicitly set it to an int 8. And the third column is of floats. The size of each of these columns is, the first column is, roughly 1/10 of a megabyte. The second column, just by setting that column to an int 8, reduced the size by order of magnitude. And the floats is the same size as the ints, even though these are obviously not repeating. Because that first column of ints does repeat, it's a strong candidate for categories. And I could, if I set that column to be a category, I have a savings in memory of 87%. But if I set that int 8, because that's actually the lowest possible it can be, it increases the size a little bit because of the overhead of categories. And since the floats, none of it repeats, it's truly random. If I set that to a category, it goes up by almost a factor of 9. And if I repeat this, just makes this like really a lot bigger, and see how it explodes. If I had 1 million rows, it's the same thing, range 1 to 4, 1 million rows, add int 8, and a float, everything moves up by a factor 10. So my first column, it's 7 megabytes of memory. The second column is not even 1 megabyte of memory, and the float's the same size as my int 8s. And I see the same savings by converting to categories, 87%. And I see no savings difference in making the int 8 into a category. And again, if I take the floats, because none of it's repeating, it just goes from 7 megabytes of memory to now 51 megabytes of memory. And it just greatly increased by using categories. Now, if I have strings, so I have first 3 rows are just of the not set as categories. And they're like days of the week, hello world that repeats, a couple of locations. And then the next 3 columns are the same as the first, but I set those explicitly to be categories. And the last string is a length of 4 random characters, and this whole data frame is 10,000 rows. So the strings with no categories takes up 2.5 megabytes. The strings with categories, because these repeat a lot, it is not even 1/10 of a megabyte. And the last is of that one column is 0.5 megabyte and this is all just 10,000 rows. So the first, if I go from categories, I drop it down by 98%, which is a lot. The second, if I set a category to be a category, there's no change of memory because it's already a category, so there's no overhead there. And that last column of the 4 random characters, if I change that to be a category, it doubles the size of that. It makes it worse. And if I expand this, to like a million rows like I did with the numbers, and so it's, the same here. You got my random string. The first two, they just go up, by a factor 10. So we got 267 megabytes down to, when you make it into categories, to 2 megabytes. And that's a huge difference savings. Again, 98% savings. Converting a category to a category, no change in savings. But look at this. When I take that last column of the 4 characters of random strings, which is 58 megabytes, when I convert it to categories, it drops it down to 47 megabytes. So what happened here? Well, an interesting fact. If you have a random string of 4 characters, and there's only 26 characters in the alphabet, so how many permutation you have is 26 times 26 times 26. So you have about 500,000 unique values. So half the string should repeat. And that's why we're seeing savings where we take that random string, quote unquote random string, and convert it into a category. Because they are repeating, it drops down in size. Now, if I increase both the length of that random string to 6, and instead of going from 4 is 6, and I make it to be 10 million rows, when I run this and save it, I'm going to create the script creates two CSV files. One that's, roughly 550 megabytes. And the last one, my awesome, it's just that first 6 columns without the random string, and it's a little less. It's about like half a gigabyte. When I read this in, I go with no categories. Again, I see that huge drop in performance, and that random string is taking up almost a half a gigabyte of memory, 600 megabytes. I see the same savings I saw before, 98.0, so that's pretty good. And when I look at that random string, that's 600 megabytes, when I convert it to category, it almost gets up to a gigabyte. It made it a lot worse because there's not enough permutation, so the strings aren't actually repeating, so categories is making it worse. So when I read in the CSV, which is, about roughly half a gigabyte, and convert it all to categories, this doesn't have the random strings. In memory, the whole data frame is 57 megabytes. So you go from 500 megabytes to 57 megabytes. You have almost a 90% increase in saving in working memory. So that in itself is amazing simply by using categories. So in conclusion, Pandas can handle data that most GUIs cannot read. Excel can tend to max out at 1 million lines. We reduce the size in working memory to less than a file size at rest. Sometimes the reduction could be as large as 90%. So categories can be helpful and they can be hurtful. So we need to take care when using them. And so if you have any questions, I'll be happy to take them. Again, the repository for this talk is located in my personal GitHub repository. And I would like to reference the following sources that I used to build this. Thank you very much and have a lovely day.